Good afternoon. Today we are going to deal with problems involving pulleys. You will see that there are quite a few of them in your pretest, and so we need to figure those out. So what is a pulley? A pulley, we've actually seen them before. We've used the little pulleys when we did the force table lab. It's basically a wheel that you hang a rope around, okay? And you can pull on this side, or you can pull on this side, or you could just hang two masses on it. But that's basically what a pulley is a rope thrown over a spinning wheel, okay? So there are a few ideas to keep in mind when we're talking about pulleys. And one of the things is that the tension force is the same throughout. So that means that this tension force on this side of the pulley is the same as this tension force on this side of the pulley. You notice this when we had the two masses hanging over, and it doesn't matter if these masses are the same or if they're different, because they're just going to pull on each other equal and opposite. So this tension force here and this tension force here are actually the same force, and that's going to be an important idea when we do this, because a lot of times we're going to be solving systems of equations. Alright, another thing we need to keep in mind is we want to have an independent free body diagram for each object, which means that, you know, if we're talking about the forces on this pink mass, we want to set up a free body diagram just for this one. Okay, so the tension force is pulling up, and its gravity's still working, so we still have our weight of our object. And then we're going to set up independent net force equations. So we're going to assume some things. If this is a bigger mass, we're going to assume that the acceleration is downwards, and then the acceleration of the other one, this one's going to pull down and this one's going to pull up. So our accelerations are going to be in opposite directions. We could also have a pulley system where, let's shrink this a little bit here. There we go. We could have a pulley system where we have a block up here on a table, and here's our pulley, and there's a rope slung over here, and there's another mass hanging down here. Still have the tension force would still be equal and opposite. Okay, notice the tension force always goes away from the object that it's pulling, so away from the object it's pulling. So if we're going to set up our net force equations, here we've got our gravity pulling down, our tension force pulling up, and we're going to assume our acceleration is down here. If we end up with a negative acceleration, what does that mean? Positive and negative in physics means yes. Okay, all it means is it's accelerating in the opposite direction. So our net force is going to be, since we're going down, this is the bigger of the two forces, so we're going to put it first, the gravitational force minus the tension force for this mass here. For this mass here, right now, if this is frictionless, the net force is the tension force, because that's the only force acting on it. So if this has a mass times acceleration is equal to the tension force. So once we know that acceleration, we know the tension force, or once we know the tension force, we can find the acceleration. For the pink one, it'll end up being our net force is, our mass times our acceleration is equal to our mass times 9.8, that's Fg, minus our tension force. Okay, so this acceleration and this acceleration are the same number. This tension and this tension are the same number. The accelerations are the same because as this block moves down, this block is moving over, and they're both moving at the same time. And so we have a system of two equations with two unknowns, so we could solve it. All right, this is a tricky one because some of our problems have multiple ropes attached to a pulley. So you're going to have to trust me on this for right now. If we do have two pulleys, do you see how the pink one has two ropes attached to it? So there's two ropes attached to this guy, and this one only has one rope attached to it. So this is going to be our basic acceleration, force equals mass times acceleration. The acceleration of this block is going to be half as big. We're going to model this. You're going to find that this isn't going to move up as fast and as far. So the acceleration of the second block is half as big as the first block because it's attached with two ropes. If it was attached with three ropes, it would be 1/3 as big. If it was attached with four ropes, it'd be 1/4 as big. So it just kind of gives you an idea of how you're going to do it. So it will be decreased by the number of ropes attached to it. So this one is attached by this rope and this rope. So it's attached by two ropes, so we're going to decrease it by 1/2. This one only has one rope, so it gets the full acceleration. This has to do with work and mechanical advantage, which we will touch on in a couple chapters, probably the next chapter. So let's apply this to one of your problems. Okay, the solution is on your pretest solutions, but I wanted to kind of work it out word-wise with you so you could see. So we have box B. Box B has a mass of 5 kilograms. So let's write that in, 5 kilograms. And box A has a mass of 4 kilograms. Okay, so our tension forces. Always going away from the object. So this one has 2 tension forces on it. And this one has 1 tension force going on it. So that's our force tension. We have 2 tension forces here. The pink one also has gravity working on it. The green one has gravity working on it. Gravity always works down. And since it's touching the table, it also has a normal force. Why isn't there a normal force on this guy here? Is it touching a surface? If it's not touching a surface, there is no normal force. So we can assume that this guy is going to slide down and it's going to have an acceleration downwards. So that would be the direction of our net force. So we've got our free body diagram for each object. Since the green one here, object A, isn't moving up and down, what can we say is true about the normal force and the gravitational force? That's right, they're equal, so they cancel out. And all the acceleration is going to be here in the horizontal direction. So these guys are going to cancel each other out. We don't really have to worry about them right now. They're not part of the issue. If there was gravity, if there was friction, then there would be. So we'll throw friction in later. This is going to be enough for this one. Trust me. So our net force, okay, our net force for the green one is the 2 tension forces. And what was true about those 2 tension forces? Remember, those are the same number. The tension here and the tension here and the tension here are all the same number because it's all one string and it's all attached together. So the tension is going to be the same here. That wouldn't be true necessarily if it was fixed at this spot here, but it's not fixed there and it's not fixed there, so we would have different tension forces. So the mass times the acceleration is equal to 2 times the tension force. Adding the two tension forces together is 2F. F plus F is 2F. So our mass is 4 times the acceleration of A is equal to 2ft. But remember what we said about acceleration? Do you see how this has 2 ropes on it? If this is our acceleration of B, how is the acceleration of A? See how the question says, think carefully about the acceleration constraint. So if the acceleration of B is just acceleration, what's the acceleration of A? The acceleration here is going to be A over 2. Okay, it's this acceleration divided by 2. So let's substitute that into our equation. 4 times, see, we could say the acceleration of A, this is the acceleration of A, this is the acceleration of B, so this is the acceleration of B divided by 2. So 4A, 4 times the acceleration of B divided by 2 is equal to 2ft. Simplifying this, we get 2 times the acceleration of B is equal to 2ft. So the tension force, this is going to make our life really easy, is equal to the acceleration of B. So that's just dealing with our pink or our green mass A. So all of this is about mass A. So far so good? So then let's do the free body diagram on mass B. Okay, mass B, the net force, since it's down and gravity works down, gravity is bigger minus our tension force. So the mass times the acceleration of B is equal to our gravitational force, so the mass times 9.8 minus Ft. We don't know what Ft is yet. Okay, so let's do some substituting. We know the mass, 5 times the acceleration of B is equal to 5 times 9.8 minus, okay, remember we said before, let's highlight this, remember we said that the tension force was equal to the acceleration of B? The tension force is equal to the acceleration of B. So we're going to substitute this in for our tension force, acceleration of B. So we get 6 times the acceleration of B is equal to 49. The acceleration of B is equal to 8.17 meters per second squared. Okay, that's the acceleration of B. Let's look at our question again. Our question says, what is the acceleration of block A? Block A. So we know the acceleration of block B is 8.17, but remember here we said the acceleration of A was half of B. So the acceleration of A is equal to the 8.17 divided by 2, which gives us 4.185 meters per second squared. closest answer, D, and it's close enough. Oh, it's actually 4.085, which makes it even better because I did try to do the math in my head. So that rounds off to 4.1, et voila, we have the answer. You will have time to ask questions. Go back and maybe re-follow through, but it is a lot. See, we had 2 equations, 2 unknowns. We didn't know the acceleration of B, and we didn't know the tension force, but we ended up with 2 equations, and so we could substitute into the 2 equations and get our answer. All right, have a great day, and I will see you tomorrow.